all this time was spent for simply just to answer that question, which is why should this be going up, right? So maybe I just take a moment to rewrite this equation so that it's easier for you to see that it is going up. And what I would do is simply take this, let me do it right here. So I copy exactly what this is in a new form, and it's increased, right? I'm going to take the equal sign and take these two terms and flow it to the other side. That's all I'm doing. And that will become in minus out, right? Did I do my math right? I told you I'm a little out of my element. So you all agree? Now can you see from here that the increase in this height increase is due to what is coming in from the top and what is going out. What coming in is bigger, right? You make $40 a week working part-time, that's coming in. And you spend $30 a week on beer.
Only $30.
So if it's 45, you're gonna have to call your parent. Right? So you get the point. So this is no different than your bookkeeping for your bank statement. Whatever left, but it's an increase. It could be negative. Do you see that now? If you see this, then you can see why for the momentum equation, the sign is what it is. Because they are parallel, they're cousins.
So for this, will it always be that in is going to be bigger than out?
No, no. No, all I'm saying is in here, whatever is inside my control volume in the increasing sign is the difference between what's come in and what goes out. Between what's coming in here, what's going out in the bottom. Just like I said before. The more easier way to visualize this is work with all positive terms, which is, let's assume coming in is greater, like $40 per week. What's going out is $30 per week. So how much does a bank account increase on a weekly basis? How much? 10. And it's positive. 10. And that's why the sign is what it is. This helps put it in a more easier way to visualize. Right? Any other question? Yes?
So your first unsteady term, what would be a case where you couldn't neglect that?
Here?
Yeah.
It's easier to see that for continuity equation. So if I have more flow coming in than that's going out, the water level will rise.
What about for the momentum?
Okay, then you have to have a different setup where you have to give me more detail as to what that unsteadiness is. And it's going to be more difficult for me to picture that with some very simple physical problem. No, I don't have an example for that unless I specify the problem in a whole lot more detail. What unsteadiness? In what functional time? Okay? So I think right now I would be more content if you simply good enough to read this equation in very plain, simple English. Actual problem, homework, there will not be anything dealing with unsteadiness. Okay? Yes? Any other question? Yes?
So I just want to clarify too, so the two equations we just derived, those aren't any different than the ones we have been using, we're just showing where they came from?
What do you mean? I'm confused. We haven't derived anything. The rental transport equation, I didn't derive that. I asked you to read it in the text. So that's fine. And then what's the next question?
So the momentum equation and the continuity equations that we just got, I guess not derived, but we have them now?
That's not derived, right.
Okay.
In the text, you are asked to read how this equation comes about. And you can do that. I mean, it will take me one lecture. It's just not that time I can afford. But once you understand this, all we did is to use it, apply it for two occasions, one continuity and the other one momentum. Now I'm going to do the third time for angular momentum. Okay, can I do that now? Right, okay, so the third application for the Reynolds transport is the so-called angular momentum equation. Or moment of momentum, i.e. angular momentum. So maybe some of you have the insight to tell me what I would want to set the capital B, which for angular momentum is still a vector. So for linear momentum, I make the capital B my linear momentum, which we did last time, right? So for angular momentum, what do you think I want the capital B to be? Anyone? So before we had linear momentum, now we do angular momentum. Anyone want to guess? Huh? Very good, very good. Radius, the radius. To get an angular momentum, I need a radius. So this would be a backyard water sprinkler. You see those before, right? You hook up to a water hose, you turn it on, and the thing just spins. And that's because of the water you go in with the momentum is changing the direction of the flow. And you don't have an anchoring force to hold it in place, you will have to just free spin. And that's angular momentum. So that is my capital B, my per unit mass simply becomes cost product of radius times the velocity, and it's all in vector quantity in ijk direction. So instead of force, so let me do the right hand side first, and you can draw a parallel with the momentum equation, rho. Now you can fill in the missing term maybe on the right hand side by extrapolating what we did on the Reynolds transport equation, first for continuity and then for linear momentum and now for angular momentum. What's the first question mark on this term? Yep, it's still out. And it's a cost product. Same with this term here. It's a cost product. So instead of force, what will be the driving potential on the left? So before it was summation forces. Say it again, please.
Summation of moments.
Moment or torque. A force times the moment. Again, it's cost product, all this are vector rotation. So this will be very useful for just that water sprinkler problem I mentioned. Anything that is axisymmetric, like a fan, the compressor or the engine, anything that is a pump that's rotating, that's axisymmetric, this equation becomes very useful. And we call those problems fluid machinery. So a month later, we'll come back and we'll do the energy. So that's the end of the formal lecture for the continuity equation, or rather chapter 5. We're done with chapter 5. That's the last piece of new lecture that I'd like you to comprehend. Do you get it? Are there any questions? So a month later, I will come back and ask you, what would you do to make the Reynolds transport equation applicable to the energy equation? But right now, let's focus on just momentum. So for that, I want to touch on the two homework. One was due 2 weeks ago, and one is due, yes?
If you were to separate that second part of the equation like you did for the previous one, what would
second part of the equation meaning, oh, you mean here? Oh, yeah, actually, that's a very good question. So before I do that, what will still this term be? It's still mass flow rate error. Doesn't matter what I have done for the random transport equation, it's still mass flow rate, right? So the question is, what would this term look like if I separate them into X, Y, Z direction? I don't quite understand the question. What do you want me to do?
The other ones you separated the mass flow rate coming in and the mass flow rate coming out. Is that the same?
It's exactly the same as first the continuity equation. So if I ask you to read that in plain simple English, you just repeat everything we have done. So for continuity, it's mass flow rate in, mass flow rate out, and it's equal to 0. For momentum, linear, is momentum in x direction, momentum out x direction, have to be balanced by the driving force, which is the force net in the x direction. Read that for angular momentum. What's driving the change of angular momentum? Again, this is all steady. In the x direction will be the net torque. In what direction? In which direction?
About the x-axis.
How about the x-axis? That will result in change of angular momentum about the x-axis for out minus in. Does that help? Does that help? Okay, good. All right, let's do some more practical problem. So both problem, the homework, the old one and the new one, worth looking at somewhat in parallel, meaning comparing them. So this, let me first make sure you all can do the homework before I go to the next step, which is slow down and smell the flower. So anyone have problem with the solution of this homework problem? And I will write out that my anchoring force, which according to this coordinate, my vertical anchoring force is assumed to be downward. That's how I've done the problem. The solution again will be posted online immediately after class. So when I get through all the algebra and apply the momentum equation as well as the continuity equation, my final algebraic expression for this anchoring force with the appropriate numerical value. So if I've done it, you can check yourself. I'm skipping all the intermediate step of starting with the momentum and continuity and just simply in nomenclature form. Mainly I want to get a feel as an engineer. You know, would I make a big mistake if I neglect at the outset the weight of the water or the weight of the nozzle? What's the answer?
Yeah. Yeah.
For this problem, you have to include it, right? Why? Because the size of the nozzle is formula. Diameter of the exit, like 6 centimeters. And the number, after you've done your engineering analysis, speak for itself. Turns out of this, about 500 Newton to hold the nozzle in place so that it doesn't fly into the sky. This 500 Newton downward. There's substantial amount from the weight of the nozzle and the weight of the water. It happened just because of the number and the angle, the momentum change is inconsequential, but you wouldn't know it until you do the math. And what is significant is actually the pressure force, right? So each problem is different, and you cannot know a priori what you can neglect. As such, I want to just revisit the old problem 2 weeks ago, of which is a 1D problem with the nozzle coming down. But in this case, the nozzle exit, instead of 6 centimeters, which is this big, how big is 2/10 of an inch? 2/10 of an inch. Quarter inch, about this big. Right? And again, you want to be safe and not jumping step. You will have to go through the entire analysis of momentum. Which you can draw a parallel. I just said the term kind of switch, but for this smaller problem, the momentum change is about 4 pound force. The weight of the nozzle, due to the size, is about 2/10. The pressure force times the area is 19, and the weight of the nozzle is even smaller. So in contrast, now they have done the problem for a tiny nozzle like fraction of an inch, what do you think you can neglect in the future? Say that again? Body force, not just the weight of the nozzle, but what else can you neglect? That of water. Right? And for this problem, turns out the pressure force again is sizable, and the change of momentum is also sizable. So I just thought at the time you're very busy just doing the homework, but I think if you slow down and look at the physics and appreciate that, so what is a good engineer versus an okay engineer? The good engineer is, after a couple of years of practice, he or she can look at the problem and say, I'm going to neglect some of this because it's inconsequential. And you get the work done in half the time. And someone had to go through the whole shebang. Right? Okay, so it's a diversion, but I thought it's worth the time. Other questions on any of the homework? Okay, so I just want to touch on the new one. Not much need to be said. And it's a 2D nozzle problem where the exiting nozzle has 2 branches. And it's water. So a lot specific in the problem I won't go into is the free jet at 2 exit, the incoming flow, some geometry is given, you are asked to find the XY forces. Let's say I have no feel for how the forces will act in the test. Is it critical which direction you assume? What if you assume this is this way? Can you still do the problem? Yes. Okay. Now the added twist for this problem is the incoming pressure is not given, but you are told the flow is frictionless, steady, incompressible. And you can assume that a streamline can be followed. What does all that mean to you? You use balloon to do what? Everything? Not quite. I guess. So you think about how the equation should be used. This is a very good example of that. How many equations you have now in your toolbox? How many equations you have in your toolbox to solve any problem I throw at you next Wednesday? 3? Which 3? In the order I want to hear. Very good. Continuity. First and foremost. You've got to write it down. Go on. what momentum? How many momentum? Two. X and Y, that's 3 equations. And then Bernoulli, so you have 4 equations. 3 is the right answer because momentum has 2 components, X and Y. Which one you want to use after continuity? Depends. Very good answer. Suppose problem like this. This one. The problem in the quiz will be like this one, except more difficult. So which one you want to use next? Which one is simpler? What are the terms in Bernoulli? Tell me. We didn't ask you. That's the next topic. So someone remind me what is in Bernoulli? Pressure, go on. What? Sorry? 1/2 V squared. Go on. Any force term? No. This is what I call closed equation. It is very simple. Pressure, velocity, and gravity. Can't get better than that. And so which one would you use next? Bernoulli. Right. Then and then you use momentum. You have to use momentum because that's the only way you can get forces. So you get it. That's logic. You're going to need that. Okay? So we'll take a break. When we come back, we'll go back to Bernoulli equation. And then the quiz. Okay?
Say what?